P1, P2, P3 are represented by X, Y and Z as the decision variables. There are two types of doll. One is A, another one is B. B is the deluxe one. One is an ordinary model, another one is the deluxe model. To determine the relevant values of the coefficients of constants involved in the LP is the main problem. Hello dear students, welcome to this session of Operation Research class or class. I am Mr. Niranjan, faculty, Department of Computer Science, Vidhyaashram First Grade College, the Temple of Excellence. In my previous classes, I have discussed regarding the formation of a linear programming problem. Today also I am going to discuss few more problems regarding the formation of a linear programming problem. Now let us consider the first problem. What is the problem given? A company manufactures, a company manufactures three types of products, P1, P2 and P3. A company manufactures three types of products, P1, P2 and P3. The profits are 30, 20 and 40. The profits, what are the profits? 30, 20 and 40. So rupees 30, rupees 20 and rupees 40. The company has two machines, that is M1 and M2. M1 and M2 processing time in minutes for each machine on each product on the total time available on each machine are given in the following table. The processing of machine 1 and the time required and the total availability of the machine M1 and M2. The products, that is the machine M1 and M2, the products P1, P2, P3 and the availability of time is given in the form of a table. Company must manufacture at least 100 P1 and at least 200 P2s and 50 P3s but not more than 150 P1s. Then formulate the problem as linear programming problem. This is very simple problem. See here, what is the given? So a company manufactures three types of products, P1, P2 and P3. Now let us consider this as the decision variables. Let X, Y, Z be the decision variables. P1, P2, P3 are represented by X, Y and Z as the decision variables. And then what is the profit given? The profits are, 30, 20 and 40. Whenever the profit is given, the function is nothing but the problem is a maximization problem. So to get the maximum profit, maximize this, that's it. So, and two machines M1 and M2 processing time in minutes is given. So that is P1, P2, P3, that is 4, 3 and 5 for M1, 2, 2 and 4 for M2. The total available time is given 2000 minutes and 5000 minutes. If such is the case, then company must manufacture at least 100 P1s, the product P1 100 and the product P2 as 200 and 3 as 50 products but not more than 150 P1. P1 should not exist more than 150. Formulate the problem as an LP model. Now let us define the decision variables as X, Y and Z. Now then, to maximize, let us define let X, Y, Z be the decision variables for the units P1, P2 and P3. So therefore, the given function is P is equal to, define this, what is that? 30x plus 20y plus 40z. P is equal to, the objective function is 20x plus 30y plus 40z. This is to be maximized. So therefore, the objective function is, this is to be maximized. Maximum of P is equal to 20x plus 30y plus 40z. This is the objective function which is to be maximized. This is the first condition. Followed. Now, what are the constraints? Now, subjected to the constraints. Subjected to constraints. Come to this. So, if I call this as X, Y and Z, then what you will get? 4x plus 3y plus 5z. The maximum availability of the time is given by 2000 for the product M1 and for the product M2 the time availability is 5000 minutes. So therefore this can be written as 4x plus 3y plus 5z is less than or equal to 2000. 2x plus 2y plus 4z is less than or equal to 5000. That's it. That can be put it in the form of, that is 4x plus 3y, 4x plus 3y plus 5z is less than or equal to 2000. And similarly, this is for the product M1, and for the product M2, this is 2x plus 2y, 2x plus 2y plus 4z, which is less than or equal to 5000 for the product M1 and M2. Let me explain once again. Let us define the objective decision variables as x, y, z. So therefore the objective function is p is equal to 20x plus 30y plus 40z. The objective function is maximum p is equal to 20x plus 30y plus 40z subjected to the constraints. So this is x, y, z for the machine M1, for the machine M1. So we are going to get the equation 4x plus 3y plus 5z. The maximum time availability is 2000. Therefore, it is less than or equal to 2000. Similarly, for the machine 2, machine M2, 2x plus 2y plus 4z is less than or equal to 5000. That is what I have written. Now further, what is given in the problem? Further, the company must manufacture at least 100 P1s, at least 200 P2s and 50 P3. So further given that the company will manufacture P1, P2, P3. What are the conditions? P1, that is 100 P1, that is nothing but x is greater than or equal to 100, which is greater than or equal to 150. Okay, next, what is the condition for y? Y is greater than or equal to, for P2 it is 200, and Z is greater than or equal to, for the product P3 it is 50. Further, what is given condition? Further, it is given that not more than 150 P1, not more than 150 P1 is nothing but 150x. Now, therefore, the given problem, the given LPP can be put it in the form. So, the profits are given to be 30, 20 and 40. Therefore, the objective function is P is equal to 20x plus 30y plus 40z. Since we are getting the maximum profit, what is to get is here the maximum profit. Therefore, the objective function is nothing but maximum P. P max is equal to 20x plus 30y plus 40z subjected to the constraints. What are the constraints here? See here, P1, P2, P3 will produce the given the decision variable for the machines M1 and M2. So, the maximum availability of time is 2000 for M1 machine and 5000 minutes for M2 machine. Therefore, this can be put in the mathematical equation for the machine M1. 4x plus 3y plus 5z is 4x plus 3y plus 5z is less than or equal to 2000. Similarly, for the machine M2, 2x plus 2y plus 4z is 5000. And further, it is given that what is the condition? The company manufactures at least 100 P1 and at least 200 P2 and 50 P3. So, but not more than 150 P1. So, 100 P1, 200 P2 and 50 P3. That is given by, see here, x is greater than or equal to 100, or this can also be written as the x is in between 100 less than or equal to x less than or equal to 150, and y is greater than 200 and z is greater than or equal to 50. Further, it is given that, what is the given condition? But P, yes, but not more than 150x, not more than 150x. So, therefore, this entire LPP model can be put in the form subjected to non-negative constraints. Therefore, the required LP model is, max P is equal to 20x plus 30y plus 40z, 20x plus 30y plus 40z subjected to the constraints. What are the constraints here? 4x plus 3y, 4x plus 3y plus 5z is less than or equal to 2000, and second equation 2x plus 2y plus 4z, 2x plus 2y plus 4z is less than or equal to 5000. Further, what is given? X 100 less than or equal to x less than or equal to 150, y is greater than or equal to 200, and z is greater than or equal to 50, subjected to the non-negative restrictions, non-negative constraints. X is greater than or equal to 0, y is greater than or equal to 0, and z is greater than or equal to 0. This is the required LPP model for this problem. That's it. It's very simple, very easy. Let us come to the next problem. The next problem is two types of hats. Two types of hat. Each hat of first type requires twice as much the labor as for the second type. So there are two types of hats. The first type of hat requires twice as much as the labor time for the second type. If all the hats are to be second type only, they manufacture only second type of hats. Let us consider the first type of hats as A and B are the two types of hats. So that is, if all the hats are of second type only, the company can produce a total of 500 hats a day. The market limits daily sales of the first and second type of hats to 150 and 250 hats, assuming that the profit per hat, or here the profit again is nothing but the maximization, 8 rupees and 5 rupees for the type A and B. Formulate the problem as linear programming model in order to determine the number of hats to be produced of each type so as to maximize the profit. So here the problem itself is given, the maximization. See here, very simple problem. A manufacturing units will produce two types of hats, A and B. What is the condition? First type of hat requires twice as much as the labor for the second type. So the first type of requires twice as much as the labor time for the second type. If all the hats are of second type only, then the company can produce only maximum 500 hats a day. But the market limits, what is the market limit here? First type will produce 150 and second type 250, assuming that the profit per hat are rupees 8 for the first type and rupees 5 for the second type of an hat. So formulate this as an LPP problem. Very simple problem. Let us consider the decision variables as x and y. What is the maximum profit here? The profit is nothing but 8 for A, rupees 8 for A and rupees 5 for B. Now let us define the decision variables as x and y. Let x and y are the decision variables. So therefore, let x and y are the decision variables for A and B. Therefore, the unit, the total number of units, the total number of units is equal to, this is x and this is y, 8x plus 5y. Now what is the objective function here? So formulate the linear programming to get the maximum profit. So therefore the objective function is max p is equal to 8x plus 5y, subjected to the constraints. Subjected to constraints. What are the constraints given here? See, the company can produce maximum 500 hats a day. Number of hats it can produce per day is 500. Okay. Now, what is the condition given? It is given that each hat of first type requires twice as much as the labor time for the second type. Suppose if T is the labor time, then A requires 2 times as that of B. That can be put in the form of an equation. Now it has given that, what is the condition given? That the type 1, each hat of first type requires twice as much labor time of the second. So each type of first type requires 2 times as that of the second type. So therefore, suppose if T is the time taken, then this can be written as 2T into X plus T into Y is less than or equal to 500, where T is the time taken, T is the time per unit. That's it. Okay. So therefore this can be written as 2x plus y is less than or equal to 500 is the labor time per unit. But further it is given that the condition of sales of the hats. What is the condition of sales of the hats? First type, the market limits daily sales the first type, and the second type has 150 and 250. So here the sales X is less than or equal to 150 and Y is less than or equal to 250. This is the given condition given. X is less than or equal to 150 and Y is less than or equal to 250. And the non-negative restrictions, subjected to the non-negative restrictions, X is greater than or equal to 0 and Y is greater than or equal to 0. This is the requirement. Now this can be put in the form. Therefore the required LP model, what is the objective function? Maximum P, max P is equal to 8x plus 5y, subjected to the constraints. What are the constraints? 22x plus y less than or equal to 150. Then x is less than or equal to 150. Y is less than or equal to 250. And the non-negative restrictions, and x is greater than or equal to 0 and y is greater than or equal to 0. This is the required LPP for the given equation, given statement. That's it. Okay. See here, very simple. So a company will manufacture 2 types of hats, A and B. Let us define the decision variables as X and Y. Since the profit is to be maximized, therefore the objective function is the maximum P is equal to 8x plus 5y. That is, maximum P is equal to 8x plus 5y, subjected to the constraints. What are the constraints given? So the time taken by the first, manufacturing for the first, is 2 times as that of the second. So therefore this can be put in the form 2tx plus ty, which is less than or equal to 500, because the company has to manufacture 500 hats per day. That is the maximum availability. So therefore T is the time per unit. This can be written as 2x plus y is less than or equal to 500. Further it is stated that x is less than or equal to 150 and y is less than or equal to 250. So, and restricted to the non-negative restrictions, that is x is greater than or equal to 0, y is greater than or equal to 0. The LPP can be put in the form. The required LP model is max P is equal to 8x plus 5y, subjected to the constraints 2x plus y is less than or equal to 150, x is less than 150 and y is less than or equal to 250, and the non-negative restrictions, x is greater than or equal to 0 and y is greater than or equal to 0. That's it. That's regarding this. Hope you followed. Now let us come to the next problem. What is the problem? A company manufactures 2 types of dolls, A and B. A and B are the 2 types of dolls. A basic version of doll A and deluxe version of doll B. Each doll of type B takes twice as long to produce one type of A, and the company would have time for a maximum 2000 per day. The supply of plastic is to produce 1500 dolls per day. The deluxe version requires a fancy dress of which there are only 600 per day available. If the company makes a profit of rupees 3 and rupees 2 per doll respectively on A and B, then how many each dolls produced to maximize total profit? Formulate this as an LPP. So again, this is nothing but an maximization problem. So here there are two types of doll. One is A, another one is B. B is the deluxe one. One is an ordinary model, another one is the deluxe model. So as that of the previous problem, here what is the condition? Each doll of type B requires twice as long as the time taken by the A. So to produce B, it will take 2 times the time taken by the product A. Now if such is the case, the company would have a time to make maximum of 2000 per day. The supply of plastic is to produce 1500 dolls, and the deluxe version requires a fancy dress of which there are only 600 per day available. If the company makes a profit of rupees 3 and 5 per A, so the profit for manufacturing of doll A is rupees 3 and for the doll B is 5, then respectively, then how many each dolls produced to maximize the profit? So here the maximization profit. This is also same as that of the previous problem. Now let us define the decision variable. Let X and Y are the decision variables for the products A and B. Now since the objective function is P is equal to 3x plus 5y. Now since it is to be maximized, therefore the objective function is max P is equal to 3x plus 5y. This is the first equation. Okay. Now what is the condition given? Now suppose let T is the time taken. If T is the time taken for the doll A and 2T is the time taken per unit for the doll B. So T is the time taken per unit for first product and 2T is the time taken to manufacture the doll B of type 2. So this can be put in the mathematical form, that is the constraints subjected to the constraints are x into t plus 2y into t. Since the maximum availability of the time is 2000, maximum is 2000, therefore this can be written as less than or equal to 2000. So that is x into t plus 2yt is less than or equal to 2000. So that is therefore x plus 2y is less than or equal to 2000. This is nothing but the availability of the time. Now what is the given condition for the plastic availability of plastic? Supply of plastic is to produce 1500 dolls per day and the deluxe version requires dress materials of 600 per day. So therefore here the plastics x plus y is less than or equal to 1500 and the dress material for the second product is y, which is less than or equal to 600. This is the constraints given. So this is the plastic and this is the dress material for type B. Okay. And since these are all positive, the non-negative restrictions are x is greater than or equal to 0 and y is greater than or equal to 0 are the non-negative restrictions. That's it. See here. So a company will manufacture two types of hats, A and B. One is an ordinary, another B is a deluxe one. So whereas each doll type B takes twice as long as to produce the type A. So therefore the profit, what is the profit given? Profit is nothing but rupees 8 for doll A and rupees 5 for doll B. Hence the objective function is 3x plus 5y. It is to be maximized, therefore maximum of P is equal to 3x plus 5y and the time per unit for A is T and the time bounded for the B is 2T. Therefore this can be written as xt plus y2yt is less than or equal to 2000 and the time is 2000. Therefore x plus 2y is less than or equal to 2000 and further the availability of the plastic is x plus y is less than or equal to 1500, and the dress material for the second type of product is dollies y is less than or equal to 600, subjected to the non-negative restrictions, that is x is greater than or equal to 0 and y is greater than or equal to 0. So therefore the required LP model can be written as, therefore the required LP model can be written as LP model is, the required LP model is, what is the maximization? Maximum P is equal to, max P is equal to 3x plus 5y, 3x plus 5y, subjected to the constraints, subjected to constraints. What are the constraints? X plus 2y is less than or equal to 2000 and x plus y is less than or equal to 1500, y is less than or equal to 6000, and the non-negative restrictions, x is greater than or equal to 0 and y is greater than or equal to 0. This is the required LP model. That's it. Hope you followed this. Now that's all regarding the example for the formation of problems. Now let us discuss regarding what are the limitations of linear programming. This is also a very important problem, a question for 7 marks. You may expect this for your 7 marks or 5 marks. What are the limitations of a linear programming problem? So to specify an object, to specify an objective function in mathematical form is not an easy task. It is not easy to form a mathematical equation, mathematical form for a given objective function. It is very difficult to form an objective function in a mathematical form. Even if objective function is determined, if you determine the objective function, it is difficult to determine the social, institutional, financial and other constraints. It is, even if you formulate the mathematical, even if you form an objective function, if the objective function is determined, but it is very difficult to determine the social conditions, institutional, financial and their other constraints. It is very difficult. Now, it is possible that the objective function and the constraint may not directly specified by the linear inequalities. This is very important a limitation. That is, it is not possible that the objective function and the constraint may not directly specified. The objective function and the constants are not directly specified in the linear programming problem, that is linear inequalities, in the form of linear inequalities in the equations. So this is very difficult. Now to determine the relevant values of the coefficients of constants involved in the LP is the main problem. So to find the coefficients of constraints, so that is to determine the relevant values, of the coefficients of the constants involved in the LP problem is very difficult. So next, the assumption of LPP are also unrealistic. It is an unrealistic method. So the assumptions are unrealistic and therefore it assumes that the factory portion remains constant. In addition, for it, the relation between the input and the output production and the cost production and the production and the total revenue are assumed to be linear. So that is the production, the cost production, production of the cost, production and the cost, and production and the total revenue are assumed to be linear. Now, and very important are, all these assumptions implies constant returns to the scale and perfect computation in the market. Therefore, in fact, the relations are not always linear and the imperfect computation prevails in the market. Now, it is very complex method. It is very complex method and it uses mathematical technique. Extensively, it requires mathematical techniques, since LPP is a complex, this is a complex method. It requires mathematical techniques extensively. So LP model presents a trial and error solution, and it is difficult to find out real optimal solution to various business problems. It is very difficult to find the exact solution, optimal solution to various business problems. So these are few limitations of linear programming problems. So that's regarding today's session. Let us meet in the next session with different problems. Thank you very much.